We also we developed a web app, a Shiny app, where all the Italian data and models for forecasting the main indicators of the epidemic are stored. What I'm going to talk about is the importance of statistical knowledge to model data in general. I just take the COVID data as an example, but we are going to talk about different aspects of statistics that often are overlooked. We're going to talk on how to communicate data, because when you communicate data, you have to put a lot of care in the message you are telling to the general public. And this sometimes, at least in Italy, it was not so straightforward. Then we move forward to the effect of a lack of statistical knowledge on the general opinions. And not only, there are some there is an economic impact of badly performed statistical modeling, which we should take into account, especially during a pandemic. Then I will talk briefly about how we managed in Italy with the epidemic and how inference statistical modeling was performed. And then I will show you, this is the more technical part, the statistical modeling, what we did, starting from very simple models from more complex approaches. I'm not aware of your statistical knowledge, but please feel free to interrupt me even during the talk if there is something not clear about formulas and others. I will conclude with some remarks quite quickly. Usually I'm the kind of statistician who prefer to start from the data. And the first thing I'm going to say to my students usually is, the data are telling us a story. Are we good enough to read it? So let's start from the data. On our, the equivalent of the BBC One, Rai Uno in Italy, the news starts in February of 2021, saying the number of new cases is increasing. So this information was at the beginning of the news, and well, of course, they would like to say, well, you have to be worried. You have to worry a little bit because there was an increase of approximately the 33% of cases from one day to another. Of course, is a huge increase, but during the same news, they also say the positivity rate decreases. Well, this is because, of course, looking at absolute numbers could be misleading. The number of new cases, of course, depends on the number of swabs. This is rather obvious. I'm pretty sure that for you is obvious, but when we communicate the data, we have to think about the general public and the message we would like to pass. The number of swabs from one day of tests from one day to another increased by 90%. And so the positivity rate decreased. So if we have to interpret the situation from one day to another, as a statistician, I would say that, well, the situation is not as bad as the first message would have said. So the first key message is we have to consider relative values rather than absolute values. But even when we consider relative values like percentages, we have to put a lot of care in the way we communicate the data. In Italy, there is a called flash survey. Yeah, there is a flash survey performed every month about the variants of concern, the variants of interest. The last one about Omicron 5 has been released at the beginning of May. Here I just show you some data about the British and the Brazilian variants. There was a huge debate in Italy about these two variants, and even the Ministry of Health did a press conference talking about these two variants as very important and dangerous. The first flash survey provided these numbers. There are regions where there is one region in which the percentage of the British variant was almost 100%, 93.3%. This region was Molise. Molise is the smallest city in Italy, is approximately 300,000 people. So it's a very tiny one. The second one, with 75%, is Sardinia. So again, not a huge not one of the largest regions in Italy. And then there is one region not affected at all by the British variant, Valle d'Aosta. Valle d'Aosta is also a tiny one up north. Why I'm saying that communicating numbers also with percentages may be quite risky? Because of course, again, it depends on the number of samples that we have analyzed. In Valle d'Aosta, for example, the FESH survey consider just one sample. So if we were lucky, no British variant at all. If we're very unlucky, 100% of people with British variant. And this is because, I will show you later in the next slide, the sampling scheme is not properly performed. But when we communicate data, we cannot really say, as the government did, that there is no British variant in Valle d'Aosta simply because the number of samples sequenced by the government in Valle d'Aosta is just one. A similar thing happened with the Brazilian variant. There is a report where there is written there is a clear geographical characterization, simply because Umbria, Toscana, and Lazio, central regions, show a presence of this variant. Of course, Abruzzo, where Mauro is also in the center of Italy, but there was no Brazilian variant. Again, the number of samples is quite small. So there is a problem of communication about the data. We have to put a lot of care when we do that, but there is a huge issue, from my perspective, in the way we perform, we obtain these numbers. I just quote from the main report: the sample has been randomly chosen by regional authorities, guaranteeing some geographical representation and, if possible, a stratification by age. Well, if a student would say something like this at my exam, will not pass it. He will fail. She will fail for sure, because when we create a sample, the sample must be representative of the population, and this is not the case. Some, if possible, are not statistical words that should be used, especially in a situation like this one. More importantly, the sampling methods used by the different regions may be different. This is because there is this health federalism in Italy, so each region is on its own, mainly from the health perspective. So the sampling method is, well, may vary. How can I make comparisons? Well, it's not clear. Consider as a further point that the sampling is not at the regional level, but the sampling scheme is a macro area level. So northeast, northwest, center, south, and islands. And then with a weird process, they divided the number of samples into the regions. So there are some problems of communications and of the way on the methodological side, on the way the survey is built. Every time we analyze data, we don't have to trust the data blindly, because sometimes the data are telling us a story which is unreliable. There is a famous book, you can find this on the web, called Spurious Correlations. It's plenty of examples like this one. If we look at the two time series, the red and the black, they are pretty much the same. I mean, it's rather clear that they are strongly correlated. But these two time series refers to US spending on science and suicides. Of course, they are not related, even though their behavior, well, they are pretty much the same. If we compute the linear correlation coefficient between these two time series, it's very likely that it's going to be very close to 1. But of course, well, they are not related. Another example, the one I prefer from the book, the divorce rate in Maine and per capita consumption of margarine. Well, again, the two time series move together, so there is a strong association between the twos, but I'm pretty sure that no one believes that the consumption of margarine would affect the divorce rate. But sometimes we have prior beliefs, and our prior beliefs drive our research. And there is a case that I would like to discuss with you about vitamin D and COVID-19. There is this quite famous paper on the role of vitamin D in the prevention of coronavirus disease in 2019 on infection and mortality. As you see, well, I just downloaded the paper again recently. It has more than 370 citations, but if you look at Google Scholar, they are double. So it's a milestone. It's been widely cited. This is the abstract. You can read it. What they do is simply comparing, well, looking for an association between the number of cases per million, the number of deaths per million, and the average level, the mean levels of vitamin D in some European countries. Quoting, the crude association observed in the present study may be explained by the role of vitamin D in the prevention of COVID-19 infection, or more probably by potential protection of vitamin D for the more negative consequences of the infection. There is a statistical problem at first, which is a bit philosophical. Correlation, so association, does not imply causation. Even if we find an association, which as we see before might be spurious, this association does not imply causation. If we read this sentence quoted by the paper, it seems instead that the vitamin D is the reason why we have less cases, less deaths. So higher values of vitamin D levels may contribute to reduce the risks. In this paper, they simply look at the association structure and not at any cause-effect modeling. This picture is taken from the paper. They also put this straight line here, like they built a regression model. I don't know if you have ever heard about regression modeling. Simple, create a model for a cause-effect linear relationship between the two variables. Any model, any test, whatever you apply in statistics is based on quite strong assumptions. When you perform a t-test, the t-test is based on some assumptions about the distribution of your data. When you build a model, linear regression model, there are the Gauss-Markov assumptions to be met and fulfilled. In this paper, there was a misleading use of statistics for different reasons. First of all, well, the reported results are a little bit masked. They report the p-value. So what they did is to perform a test on the correlation coefficient, reporting the p-value. They report a p-value of 0.05 in both cases. So looking at the correlation between deaths and vitamin D levels, cases and vitamin D levels. But as you see, the nominal value is a little bit higher than the 5% level, often taken as the significance level. We can discuss about the importance and the use of the p-value. There is a huge debate from the American Statistical Association and on the Biometrical Journal on the role played by the p-value in medical statistics, which is quite a huge debate. But you know, this is the first step of the way statistics can be used just to confirm a prior belief. I believe that there is a relationship. Well, it's a little bit above of 0.5, so 0.05. So I just adjust a little bit the numbers. But any test must fulfill some assumptions. In particular, in this case, the data must follow a Gaussian distribution, the Bell distribution, right? If they don't, well, the results that you get from any test are useless, cannot be used. Moreover, in the data, there is something called heteroskedasticity. So the variance is not constant. If we look at the graph, you can see here that the variability is much higher for low levels of vitamin D and much smaller here on the right tail of the distribution. There are outliers, and they can significantly affect your results. moreover, and this is something to me quite funny, but at the same time, it gives you the idea of, well, when you apply statistics, you have to check your results. You have to check that your results make sense. If we assume a linear cause-effect relationship, so if we consider this relationship displayed by the dashed line, we obtain some fitted values. So the values of the number of deaths, for example, according to our model for a specific value of vitamin D levels. Well, in Slovakia, according to the model, we would have minus 16 deaths per million population. So it's like people, it's not as resuscitating. I mean, of course, this value is completely unreliable. There is also a misleading use of the data. I mean, there are two letters written to the journal. One is mine, where I describe the misleading use of statistics, and another one describing the misleading use of data by another guy. Simply show that the data are too heterogeneous. The way deaths are computed in the different countries is heterogeneous. Well, there are some problems. For example, also some data were relatively old, I mean, from the 90s, referring to Switzerland, or 2007, referring to Turkey. Well, believe me or not, my letter where I explained the misleading use of statistics probably has 3 or 4 citations, and it's pretty much the same for this other letter explaining the misleading use of the data. 373 citations and more than 700 on Google Scholar. So the lack of statistical knowledge may produce a bias in the research, but at the same time, in Italy, there was the newspapers talked a lot about the effect of vitamin D, and there was an increase in the selling of vitamin D in Italy. So someone made money out of it. Of course, the management of the epidemic is not based on correlations only. In Italy, the government tried to introduce a quite, more complex approach to manage the epidemic. This approach was mainly focused on what is called the reproduction number, RT. According to the values taken by the reproduction number, we created the white, yellow, orange, and red zones with some restrictions. Newspapers, I'm sorry, they are in Italian, I'm going to translate them. The RT index is decreasing, but Basilicata, one of the regions in the south, has the highest value. Veneto is a yellow zone for the 3rd week in a row, but its RT value is the worst with Basilicata. Well, the point estimate, RT is not something we observed. We need to estimate this reproduction number. Along with all the estimates, the point estimates are surrounded by some uncertainty measures. In this specific case, we see that Basilicata and Veneto have pretty much the same point estimates. So the reproduction number, the point estimate of the reproduction number in the 2 regions is pretty much the same. But the uncertainty measures, so these are the credible intervals, are completely different. Just to give you an idea, if the reproduction number is greater than 1, then the epidemic is growing, and otherwise, if it's less than 1, it's decreasing. For Veneto, the entire interval is above 1. So the reproduction number in Veneto is statistically different from greater than 1. So the epidemic is spreading, is growing. In Basilicata, this was not the case, because the credible interval include the value 1. So it could be 0.7, from 0.7 to 1.7. So the situation could be very heterogeneous. So in Veneto was at risky at that time, while Basilicata was not. How did it work in Italy? This reproduction number was estimated simply using an R package. R is a very famous statistical software, freely available. And there are some packages available for the users. The most famous to deal with epidemiology is EpiEstim, which is referred to a paper by Cori et al. Focusing really just on the estimation of RT. When we estimate RT, we need to take into account three different aspects of the data. The time window defined to estimate RT. If we take a short window, then data will suffer by noise. So even a small change in the data will produce a huge change in the estimate of RT. If we take a longer period, then we have a smooth effect. So it's not so straightforward to define the time window. There are some criteria, some suggestions in the reference paper by Cori. The distributions, so RT refers to the number of cases. The number of cases is can be represented by a count variable. The most famous count distribution is the Poisson variable, but the Poisson has a quite strong assumption. The mean, the expected value, and the variance. So the mean and the variance are exactly the same under the Poisson model. In the data, this is not the case. There is what is called over dispersion. So the variance is much higher than the mean. And then the crucial assumption, the generation time. So the time that an infector infects an infectee. So just the time required for me to infect someone else. This is not observed and must be estimated. In Italy, is estimated according to these data that you observe here. So the pink bars are the observations, and the blue line represent the gamma distribution. And well, the guys providing the estimates for the government believed that the histograms, the bars, can be approximated reasonably well by the blue line, which is a gamma distribution. Well, you don't have to be a statistician to see that the blue line is not really approximating in a reasonable way the pink bar. You can see there are some modes here on the right tail. It seems that the distribution is multimodal, multiple modes, and this is completely ignored. Moreover, believe me or not, the generation time, so the crucial ingredient to estimate the RT, has been estimated on 90 pairs of cases. 90. I don't know how many millions of cases we have now, and still it has never been updated. The generation time in Italy is still referred to 90 pairs of cases observed in Lombardy in February 2020. Okay, so at the beginning of the epidemic. This estimate was taken for granted for all Italian regions, large regions, rural regions. So, and the effect is the following: a lot of uncertainty in the estimated values of RT. For example, in Molise, tiny regions, as we said before, RT could be less than 0.5 of close to 2.5. So Molise will explode, or well, is in a safe condition, who knows? The problem was that the point estimate of RT was largely taken as the guidance indicator to decide restriction, to impose restrictions. So for example, Molise in this case was in the orange zone. After a while, they realized that probably the point estimate was not correct or was too uncertain. So in Italy, we start looking at the lower bound of the credible interval. As a statistician, anyway, when I see such a huge uncertainty surrounding an estimate, the first thought must be the model is not suited for the data attempt. And this was the case. If you use information taken from Lombardy on 90 people on February 2020, and you apply that hypothesis on all the regions, which are very heterogeneous, the risk is that you have a lot of uncertainty surrounding your point estimate, simply because the assumptions you are making are not reflected in the data you are analyzing. And this is where the statisticians come in, and I will show you some methods we used to avoid what you see in this slide. Again, I'm sorry, it's in Italian, I will translate, but the idea is that unreliable predictions make people worry. Here, there was a famous physicist, a physicist who went often on TV, simply saying the fourth wave has an exponential growth and it's not going to stop on the 30th of July. So this dashed lines is on the 30th of July. The red points are the observations. The blue line is the exponential growth. Well, we have to put a lot of care when we make predictions, forecasts, because then people is worried, but people then believe that we are like magicians. We simply say something just to go on the newspapers, but this was not the case. And this is because the model was wrong. Well, here it seems that for a while the distribution was exponential, but as you see, the peak of the fourth wave was the 1st of August. We entered the peak phase at the beginning of August. So this prediction was completely wrong. There are other main errors when approaching COVID-19 data. First of all, we are working with counts 0, 1, 2, 3, 4. So they are discrete values. Often these values are treated as continuous, and this is wrong. Sometimes, and this is what happened to me recently. I'm reviewing a paper now, and they transform the data to apply a very well-known and well-established method approach. So the idea is, I know a method, I believe that this method might be suitable. I transform the data in order to apply a method. Well, usually we do the opposite. We find the best method to capture, to model the data features. One way of transforming the data, the simplest, is simply taking the log of the counts and then assume that they are Gaussianly distributed. But there is a problem. This is a technical issue, I must say. In count data analysis, the mean and the variance, as I mentioned before for the Poisson, are somehow linked. In the Poisson, they are really the same under the Poisson model, but in general, they are linked. High counts, high variability, low counts, low variability. If you assume a Gaussian distribution, the mean and the variance do not fulfill this relationship. They are not linked. Then we are working with time series. So the time dimension may also play a role, and this is often neglected. Observations are often assumed to be independent. A good fit does not imply a good forecast, and this is the example. A reasonably good fit does not imply a good forecast. And of course, I read predictions up to 2025 unreliable, or also some predicted scenarios were presented also by the government. But if none of those happen, then maybe your model should be revised. And again, this is where statisticians play a role. For example, we provided a model for ICU occupation, a very simple model. We would like simply to forecast at the very short term the number of occupied ICU beds. This is because, especially during the first wave in some regions, there were no beds left. So we would like to create a sort of alarm system for the regions in order to move patients to other neighborhood regions, avoiding too much pressure on the health system. The method, it's very simple, because sometimes the solution is not to have a very complex model, a very flexible model, a model which accounts for everything. The model must be effective. Our model is based on two approaches. a Poisson regression and a time series regression. We have these two approaches. The time series regression was created to account for the time dimension of the data. The Poisson model, the Poisson mixed effect regression, was created to account for heterogeneity across regions. I skipped the formulas. The two models are very, very simple. You see here, we are simply saying that the average number of ICU hospitalizations depends on the previous one plus the previous mean plus the previous observations plus some other covariates. Everything is so simple. And then we merge them, we merge the estimates under an ensemble approach. So we take the estimate, the forecast from the Poisson mixed effect regression model and from the autoregression time series modeling, and then we weight them. Of course, it's crucial the way we choose the weights. We don't choose any weights. We simply look at it's called the leave last out predictions, and we solve an optimization problem. So we try to find the best weight in terms of prediction. So we consider, it's called the rolling window. So we just checked that our estimates were reasonably good. Results were very good. The daily absolute error has a median of 4 bets, so plus or minus 4 bets, and the quartiles are between 1 and 8 bets. So we believe that it was quite fine, and 99.4% of times over 840 intervals, the observed number of ICU hospitalizations were included in the intervals. This is just an example of 3 regions, and we can take the upper bound of these intervals as an alarming tool, an alarming system. If the upper bound of this interval is greater than the number of available beds, then we might have a problem. If we would like to model the epidemic, we should know that the curve of cases, but also deaths, has some specific data features. And then I will skip most of this, but there is an increasing part, then there is a peak, and then the decreasing part, but the growth and the decrease might not have the same rate. So there are several characteristics. Well, there are also asymptotes, so fine. So there are some characteristics intrinsic in the data. We don't want to modify the data to apply well-known methods. We would like to find a distribution, a model, which is able to capture, to approximate the main data characteristics. In this case, we consider the Richards curve, also known as generalized logistic regression. Because this approach, the Richards curve, has some parameters which are able to capture the growth rate, the peak, and so forth. We use this approach to predict the peak. I skipped most of this. What was also very important, at least in Italy, it was that there was a sort of contagion effect across areas. We don't believe, except during lockdowns, that the epidemic, the virus, didn't spread all over because there were contacts between people, across people. And contacts could be of different kinds. Well, we can consider similarities based on geographical positions of the regions, or looking at proximity flows. Just to give you an idea, on the right, you have proximities based on regional positions. So from Lombardy, you have connections with Piemonte, Emilia-Romagna, Veneto, and Trentino. But the truth is that we might assume a more complex spatial dependence, represented by the graph on the left, based on proximity flows. So the correct way of modeling the spatial dependence is through proximity flows. These flows are based on rail connections, flight connections between regions, and so forth. If we further account for spatial dependence, we have increased the accuracy of our point estimates. These are just some examples. Instead of using the Poisson model, we use the negative binomial because the negative binomial allow us to account for over-dispersion, variance greater than the mean. Other examples, this is our Shiny app. The Italian version has been updated daily, the English one once per week. There are all the information about the Italian situation. There are the short time forecast based on the ICU models I show you. There are the medium term forecast based on the Richards curve, and there are information also about the vaccinations. It's quite effective. Journalists and the general public have used this Shiny app since 2 years. You can find all the information from Italy. All the data from Italy are stored there. There are nice graphs and many other things. Just to conclude, when we talk about statistics, we don't have, well, our research should not be driven by our prior beliefs. If we have prior beliefs, the risk is that we are looking for these beliefs in the data. And we cannot say that the model is correct and the data are wrong because our analysis produces results that are not in line with our thoughts. This is what happened. Many people used compartmental models, SIR models, which are great models if the data are somehow clean. We are working with dirty data. It's difficult to use the models that are based on quite strong assumptions, and then the data are telling us a different story. The major problem with non-statisticians is that they don't know too much about statistics, but they believe that the statistics they know is enough to be a data analyst. This is not true. And of course, even these two models I show you on ICU and on the Richards curve are valid. They provide a reasonable forecast, but they are not valid in general. They should be updated according to specific data characteristics. If you have multiple waves, for example, well, the Richards curve should be adapted because the Richards curve could go only up and down. It cannot go up again unless you modify a little bit your approach. So the one model fits all theory does not work in statistics. If you're interested in what we are doing, what we have published of the papers we have published in the last couple of years, they go from statistical methods to some papers about how to communicate the data, to, well, one I didn't mention is the one with Dan Maboning from the University of Southampton, where we estimated the number, well, we call the dark number. So the number of undetected infections, which was a big issue, especially at the beginning of the epidemic in early 2020. So we provided an estimate of the unobserved, undetected infections in several European countries using a capture-recapture approach. And that's it. Thank you very much.